So there are three main criteria to have a buffer solution. A good buffer solution should have criteria number one. You must have a weak acid and a weak base. They are conjugated to one another. A few examples here. So all these things are a possible buffer combinations. The basic thing for this is actually it must contain the conjugated acid-base pair. First one is actually HF. That's actually your weak acid. And a NAF. Every time you see NAF, you should know that it is a salt. And the things that is actually relevant to your pH is F minus. Train yourself so you have the eye to see this. Then you can see that HF and F minus, they are conjugated acid-base pair. Therefore, you can have a buffer solution. The same thing for this, right? HCN is a weak acid. And the NaCN is equivalent to Cm minus. So you have HCN, Cm minus. They are conjugated acid-base pairs. Every time you see a conjugated acid-base pairs, the word that should pop up in your mind is buffer solution, buffer solution, buffer solution. Okay? So you can do this practice here. One thing that's a little bit special that students will actually miss is that the amine group, for example, this guy, NH4Cl, you should see this as NH4 plus Cl minus is a conjugate base of a strong acid, right? So this guy did not actually contribute to your pH. So the remaining part, which is actually NH4 plus, is a conjugated acid of a weak base. Okay, so that is the acid you have, and then NH3, that is the weak base you have. This is also a conjugated acid-base pair. This is actually a good combination for a buffer as well. Sometimes you will see it doesn't really write out as NH4 plus. It writes out as these things like CH3, NH3. So what this means is actually, if you look at this structure, it means your nitrogen attached to 4 hydrogen. Oftenly in your homework, you will see something like this, like CH3, CH3, CH3. This is actually the same as your NH4 plus. Okay, sometimes the nitrogen doesn't have to be always attached to a hydrogen. Okay, you can attach to a alkyl chain, and then you can attach to like 1 alkyl chain, 2 alkyl chain, or 3 alkyl chain. But the things you should see is actually all these things is actually belongs to so-called the amine base. Every time you see this, a chemical formula that give you N attached to maybe 4 different atoms, okay, with a plus, okay, that is actually a weak acid. All right, so let's actually the first criteria, and you really need to actually have a conjugated acid-base pair. Criteria number 2, this weak acid, weak base, they should actually have more or less the same amount. If there is so much acid than the base, then you won't actually make a good buffer, because it means actually if there's so much weak acid, then it has a good ability to actually buffer strong base. It doesn't actually going to be effective for your strong acid. So the criteria number 2 is actually your acid-base pair should actually have approximately equal amount. Criteria number 3 is actually they must be in substantial amounts. In other words, both species need to be in high concentration. When I say high concentration, typically is in the millimolar concentration. Right now we're going to go to the most important equation of this chapter. Every time you see you have a buffer solution, this will be the go-to equation you want to use. For example, today you have this weak acid, and it's going to dissolve inside your water, okay? And then you have a substantial amount of weak base coexisting inside your solution. Then you know your Ka was defined as H plus concentration times A minus concentration over HA concentration, right? So once you have these definitions, I can actually rearrange this equation so that I can actually express my proton concentration is going to equals to, I'm going to move these two to the left. On the top will be the Ka times your HA concentration. At the bottom will be your A minus. Then I want to actually convert this one into my pH. So we know the pH is simply a negative log of proton concentration. So I'm going to take the negative log on both sides. So that I have negative log H plus is going to equals to, okay, I want to put these things in one term and let in another. So you'll be negative log Ka plus negative log acid over base. On the left-hand side, we know that is actually your definition of your pH, right? And then if you do the negative log of your Ka, this is actually a definition of your pKa. Okay, so if you expand this one, it will be pKa minus log your acid concentration over your base concentration. And you got to these final equations that we are going to use over and over again in this chapter. This equation was actually derived by two scientists, okay, Henderson and then Hasselbalch. Okay, we are going to refer this as HH equation. That is actually the equations that you need to memorize. Okay, so the HH equation is the most important equation for this chapter. Based on this equation, you can see that, okay, when you throw in an acid or base into a buffer, it's going to change its relative concentration between your weak acid and weak base, right? So that they will actually eventually change your pH of your solution. Get back to this. How do you actually prepare the buffer? So for example, here I say, can you actually design a buffer or can you prepare a buffer with pH of 4.6? The way you prepare a buffer is what? You first need to actually create a situation that you have your conjugated acid and base pair, right? So if you look at this HH equation more carefully, if you add in the same amount of HA and A minus, then the second term will be negative log 1. Then your pH will purely determined by the pKa of your substance. So the first thing you do is actually, okay, that is your target pH, right? So you want to find a system has a pKa that's very close to your pH. So if you look at the table you have, okay, you want to find a thing that's close to 4.6. Probably this guy will be actually your choice, right? The acetic acid with pKa of 4.75. Let me blow this up a little bit more for you. So you can see the pKa of acetic acid is 4.75, right? So you start from there. Therefore, you know, pick up the conjugated acid-base pair based on their pKa, right? So we know we want to pick HCOOH and the HCOO minus. Typically, the source of HCOO minus will coming from the salt. Okay, so typically the things you're going to buy is something like this. The conjugate base with 1A group type of salt. Okay, then you can control the concentration of this very well. And then you just add in substantial amount, okay? You can add in 1 more, 2 more, 3 more, it doesn't really matter, okay? As long as your conjugated acid-base pair, they are the same concentration, then the second term will not affect your pH. So once you prepare that, okay, you're going to have a solution with a pH of 4.75. So it's higher than your target pH, 4.6, right? So what do you do afterward? What would you do? How can you actually decrease the pH of a solution? Yes, you add in strong acid. Okay, you add in high concentration strong acid so that you will tune your pH just a little bit. Okay, so this is actually by adding in either strong acid or strong base. So it's less simple. Okay, so when you prepare the buffer solution inside the laboratory, okay, it's really like you check out the pKa table, you identify what species you want to use. You store in tons of land into your water. Then you finalize pH by adding in your strong acid or strong base. One important term that you need to know from here is actually so-called the buffer capacity. Remember, that's actually one criteria we say the buffer must have is actually your conjugated acid base need to be in a large amount, right? Because only when you have a large amount of this conjugated acid base, they can actually start to interact with your strong acid base to minimize the change of your pH. If today you only have like very small amount of the conjugated acid base inside your solution, then it can only handle a very small amount of strong acid or strong base added into your solution. The buffer capacity is basically going to indicate the amount of your conjugated acid base. Okay, you want to have really high concentration of your conjugated acid and base pair inside your solution.